In today's video, we'll be discussing acceleration, which is one way that we can describe changes in an object's motion. So let's look at a few examples of acceleration to try to piece together what it might mean. So here we see an example of acceleration with this guy popping the wheelie on his motorcycle. Another cuter example of acceleration here is this pup running down the hallway. And here we see a satellite orbiting around the Earth. So take a look at these, maybe pause the video and see if you can maybe come up with your own definition of what you think acceleration might be using these examples. So what do you think? What is acceleration? So when we say acceleration, we are defining it as any change in an object's velocity. So we remember that velocity describes how far an object travels per a given unit of time and in what direction. So when we say a change in the object's velocity, what can that mean? This can mean one of three things. First, this can be increasing speed or speeding up. This is probably what you think of when you hear the word acceleration, because generally when we use it in day-to-day life, we are talking about positive acceleration or speeding up. This can also mean decreasing speed or slowing down. This is what we call deceleration. Finally, acceleration also represents a change in an object's direction. So even if its speed is staying the same, if direction is changing, that also is considered a form of acceleration because the velocity is changing. So here's an example that we looked at of increasing speed or positive acceleration. This bike is starting from a lower velocity, and as he accelerates or as he hits the gas pedal, his speed is increasing. Our second example, our cute little pup, we can see that as he runs down the hall, he's traveling at a certain velocity and is able to decelerate or slow down until he's at rest. Finally, our third example of the satellite orbiting the Earth is potentially the most important for us to discuss. As we can see in the video, and as you might suspect, the satellite is traveling at a constant speed. It's orbiting at one given speed. However, it's constantly changing its direction as it orbits in this circular direction. That means that even though the speed is constant, it is accelerating because it's experiencing a change in direction. Now, in order to calculate acceleration, we of course need to know our acceleration formula. So, if we think about acceleration in terms of speed, we can think of it as a change in an object's speed per unit time. So for that reason, our acceleration formula makes sense that it is acceleration being equal to the final velocity minus the initial velocity divided by the change in time. This means that acceleration is equal to how much that object's velocity changed over a given period of time. We'll write this out using our abbreviations. We see that the formula is A equals VF minus VI divided by delta T, delta meaning change. This is how you will most commonly see the formula written out. And the units for acceleration, if you look at your formula, you will see that I have a velocity on top and a time at the bottom. That is a meter per second over a second, which leaves me with meters per second squared, which are the units for acceleration. Now that we know what acceleration is and the formula we need to calculate it, let's go ahead and look at a few examples of actually using our formula to find object's acceleration. So in this first example, it tells us that a roller coaster car rapidly picks up speed as it rolls down a slope. As it starts down the slope, its speed is 4 meters per second. 3 seconds later, at the bottom of the slope, its speed is 22 meters per second. What is the average acceleration? So in order to break down this problem, let's think about what information we're given and what information we need to know. So we know that we're being asked for the average acceleration. We also know that acceleration is equal to final velocity minus initial velocity divided by the change in time. So in order to solve for acceleration, I will need to know all of these different terms. So let's go ahead and break down our word problem to see if we can find that information. So First, we're told that the car is rapidly picking up speed as it rolls down a slope. As it starts down the slope, we're told that its speed is 4 meters per second. So the word start here tells me that this is at the beginning or initial velocity. So I can immediately notice that I do know my initial velocity and that it is 4 meters per second. Then tells me 3 seconds later at the bottom of the slope, its speed is 22 meters per second. So here we can see that it's after 3 seconds, its speed has now increased to 22 meters per second. That tells me that the final velocity over this period of time is 22 meters per second and that the time of travel was that 3 seconds. So now that I've identified all of my known information, I'm ready to simply plug it into my formula and solve. So again, we always want to start with our formula, which in this case is A equals VF minus VI divided by delta T. We already have picked out our knowns, so we know that my VF, or velocity final, is equal to 22 meters per second. My initial velocity is equal to 4 meters per second. And my time is equal to 3 seconds. So now all I need to do is put this in my calculator. I know that 22 minus 4 is 18. If I divide 18 by 3, I don't really need a calculator for that. I know that it is equal to 6. I know that numbers mean nothing in science without units. So if we look, we have meters per second over seconds, which we know leaves me with meters per second squared. So we know that this roller coaster car has increased its velocity by 6 meters per second. So it has accelerated at a rate of 6 meters per second squared, positive. Let's look at another example here of calculating acceleration. This tells us that a cyclist accelerates from 0 meters per second to 8 meters per second in 3 seconds. What is this acceleration? Then asks us, is this acceleration higher than that of a car which accelerates from 0 to 30 meters per second in 8 seconds? So, again, we know that A is equal to VF minus VI over delta T. So first we want to start with my cyclist. I'll put that over here. So with my cyclist, I want to find his final velocity, his initial velocity, and his time of travel. So here it tells us that he is accelerating from 0 meters per second. The from tells me that was what he had at the beginning. To tells me that's the final 8 meters per second. It also tells us that it took him 3 seconds to do this, so we know that my time is 3 seconds. Let's talk about the car. VF of the car, VI of the car, and T of the car. Here this tells me that the car is accelerating from, again, 0 meters per second to 30 meters per second. Also, we're told that it takes 8 seconds. Now we're ready to simply, again, plug in and chug and solve for some values here. So let's start with the cyclist. Go ahead and just label it the same way over here. So again, we know that A is equal to VF minus VI over T. Go ahead and plug in. My VF is 8 meters per second. My VI is 0. And we want to divide that value by 3. 8 divided by 3, we'll stick that in our calculator. We get 2.66 repeating. I will round that to 2.67. And my units are meters per second squared. Now let's go ahead and do the same for our car. I've already written my formula, so I'll just go ahead and plug for the sake of time. We know that VF is 30 meters per second, VI was 0, and the time was 8 seconds. So 30 minus 0 is 30 divided by 8 gives me 3.75 meters per second squared. So looking at my information here, we can say that the car is accelerating at a greater rate or at a higher rate than the cyclist. Here we'll look at another very important example. This tells us that a brake company advertisement states that a certain type of brake can decelerate a car from 700 meters per second to rest in 7 seconds. Find the car's average acceleration under these circumstances. So just for good practice, I will continue to write out my formula, even though at this point you're probably like, I got it. So we want to look and see if we can find our VF, our VI, and our time. So in this case, we're told that the car is decelerating. We know it's a brake, so those are meant to slow something down. So we should keep that in mind as we start to solve our problem. So we see from 700 meters per second to rest. That tells me that my initial velocity 700 meters per second, and it is going to rest, which tells me that rest is its final velocity. When I say something is at rest, it's not moving, so its velocity must be 0. Finally, we're told that it takes 7 seconds to do so, or at least that's what the advertisement says. So now let's go ahead and plug in and see what happens here. So we know, again, that A is equal to VF minus VI over T. My VF here is 0 meters per second minus 700 meters per second divided by 7 seconds. Now here's where we want to make sure we're paying close attention to our math rules. So 0 minus 700 is not 700, it is negative 700. So in my numerator, I have negative 700 meters per second divided by 7 seconds. That means that my answer is negative 100 meters per second squared. So in this case, we see that we get a negative value for our answer. When I see a negative acceleration, that means that it is decelerating, or its velocity is decreasing, going in the negative direction. That makes sense because we were told that these are brakes. They are made to decelerate or slow down a car. So now we know that if I see a negative value for my acceleration, I know that that means that the object is actually decreasing its speed or decelerating.